Hello, today I'm going to solve a third order initial value problem for a linear homogeneous ODE with constant coefficients. So this is an initial value problem because it is an ordinary differential equation plus initial conditions. You know, 3 is wild here. 3 is the big number. 3 primes is third order ODE. 3 initial conditions, and later we'll find 3 constants, C1, C2, C3, 3 equations and 3 unknowns. All right, so the first thing we're going to do, because this is a linear homogeneous ODE with constant coefficients, we say that a lot, is write down the characteristic equation. You might remember you plug in y is e to the kx. And some people plug in e to the rx. And when you plug it in, every term has e to the kx factor, but this has a k cubed, a k squared, a k, and a nothing from the derivatives. So you get the characteristic equation, k cubed minus 7k squared minus k plus 7 equals 0. I'm going to circle that. That's the characteristic equation. Okay, very important. It's really quick to get. You might want to show the rules, and I've done that in class. I mean, show the steps when you plug it in, and then you factor out the e to the kx, etc. All right, well, wow, solving a cubic polynomial equation is in general basically impossible. There's this Renaissance dude who came up with the formula, but you wouldn't want to do it. The only hope you have is that the polynomial factors, and of course, it's going to factor because we always give you doable problems, right? And also notice the similarity. This is sometimes called factoring by grouping. Those two terms and those two terms look kind of similar. In fact, if I pull out the k squared just from the first two terms, I get k minus 7. And then I pull out a k minus 7 from the last two terms, and I get a minus times k minus 7 equals 0. All right, oh, that's good because the k minus 7 is in both of the terms. So this is k squared minus 1 times k minus 7 equals 0. So I found one factor. Now it's just a quadratic. And if it's a quadratic, you can, if you have to, use a quadratic formula. But we can do a lot better than that here because it's k plus 1 times k minus 1 times k minus 7 equals 0. So that fully factors. And if you couldn't do that, I have a little hint here. I'm going to share the screen. I actually looked at this on Desmos. I actually graphed z equals k cubed minus 7k squared minus k plus 7. You can do this on your calculator too if you want. And you notice the intercepts, the k-intercepts, and usually the x-intercepts, the k-intercepts are minus 1, 1, and 7. So cool. So if you're hoping that you have a cubic that factors, you can always graph it. Remember, the factors, like k plus 1, corresponds to the root k equals negative 1, right? So the 3 roots of the characteristic equation are negative 1, 1, and 7 are the roots of the characteristic equation. All right, so far, things are working out nicely, okay? And if it doesn't work out nicely, you're probably doing something wrong. Unless you're in the real world. Like if you got a job, things aren't going to work out nicely. All right. You got a job as an engineering firm or something. All right. So actually I can actually erase everything but these roots now and write down the general solution, right? Because this is usually not a solution to the difference equation, but it is if k is -1. This is a solution if k is 1 or if k is 7. And that's the whole idea. And we get the general solution by taking a linear combination of those three solutions we just found. So get rid of all of this except for the result of the general solution, except the result of those three roots. So we take those three roots, we turn them into the general solution. Okay, and you can write this in a lot of different ways. There is only one general solution that is a three-parameter family of functions. However, you can write it in different ways, right? One of the easy ways, I could call the coefficient of that C1, the coefficient of that C2, and that C3. I could call the different C1s, relabel them, but even more than that, there's other ways to do that. But this is probably what everybody would do, except for maybe a reordering of those three functions. All right. So now we're ready for now we're ready for the initial condition, right? This is a general solution to the ODE. Now we want to find C1, C2, and C3 such that all these things hold. All right. So right underneath this, I'm going to do y prime. Okay, so y prime is -C1 even negative x, right? Because I know the chain rule forward and backward, and know the differential exponentials, plus C2 e to the x, plus 7C3 e to the 7x, and y double prime is plus, because negative is a plus, e to the minus x, plus C2 e to the x, plus 49 C3 e to the 7x. Cool. All right. So now, using the super important fact that e to the 0 is 1, okay, I'm going to translate these three initial conditions into three equations for C1, C2, and C3. If I plug x equals 0 here, I get C1 times e to the minus 0, C1 times 1. So I get C1 plus C2 plus C3 equals 3. That's the first initial condition. Second initial condition is negative C1 plus C2 plus 7C3 equals -9. Okay. All right, that's that's ITS for you. Okay. I hope that you're probably hearing all these beeps. Okay. Wow. Yeah, USB drive. Okay. Then the third one is that C1 plus C2 plus a whopping 49 C3 equals -93. Okay, so this is the three equations for the three unknowns C1, C2, and C3. All right. I'm not going to erase this general solution because I'll need it later, but I can erase the other stuff. Don't really need this anymore. Don't need those anymore. In fact, just a hint while I'm erasing. You're going to want to be able to go back and forth between this general solution, the roots of the characteristic equation, and the ODE. They're all sort of, from any one, you can get the other, basically. And we're going to be doing that later. All right. But to solve these equations, I'm going to give them names. I'm going to call that A, B, and C. So we have equation A, equation B, and equation C. Okay. Now, in general, three equations and three linear equations and three unknowns is pretty hard to solve. But again, just like solving a cubic is hard, there's probably some trick. And oh, there is a trick. Look at that. Those are exactly the same. C1 plus C2, C1 plus C2. So if I took that one and subtracted that one, okay, or the other way around. Let's just take the first equation minus the third. And the way I write that, and let's remember, we want to save that. We're going to need that later. We take A minus C. What do I do if I get equation A minus equation C? I get 0 C1 plus 0 C2. And that's why I did that. That's why I subtracted them. Okay, plus 1 minus 49 C3. And that's going to be equal to 3 minus negative 93. Okay. Okay, so that's 0, this is going to be a minus 48 C3 equals plus 96. 48 plus 48 is 80 plus 16, 96. C3 is negative 2. Cool. And now that C3 is negative 2, I can take equation A with C3 is negative 2, and I get C1 plus C2 minus 2 equals 3, and equation B with C3 equals negative 2, and I get negative C1 plus C2, minus 14 equals negative 9. Okay. Or how much room do I have on the right? Maybe enough. C1 plus C2 equals 5. Bring that over. Negative C1 plus C2 is going to be 14 minus 9. That's 5 as well. So that's now a pretty easy system of two equations and two unknowns. I can add them, and I get 2C2 equals 10, or C2 is 5. And now that I have C2 is 5, I can say C1 is 5 minus C2, which is 5 minus 5. C1 is 0. Cool. All right, so I know that we have our general solution. And by the way, I know there's definitely a tendency to say, oh, great, I'm done with the problem, move on to the next one. And I would, I usually give 6 points on an exam problem. If you stopped right now and did everything right, I would give you 5 out of 6 points, maybe even 5.5 out of 6 points. By the way, this is a lot harder than anything I would give on a test. This idea of that trick of factoring in three equations and three unknowns. No, even with that trick, I wouldn't make you do that. But let's remember that we've got C1 is 0, C2 is, where is it? 5, and C3 is negative 2. So now the solution to the IVP is what I get if I plug these C's back in there. solution to the initial value problem, the ODE plus the initial conditions, is y equals, I can leave out the 0 times e to the minus x, 5 e to the plus x, minus 2 e to the 7x. Okay. So that's the way all of these go, really, when you have a linear homogeneous ODE with constant coefficients plus initial conditions. There's a very important number, the order. Here the order is 3. 3 primes is the highest primes, 3 initial conditions. Degree 3 characteristic equation, 3 roots. Now, in general, you're going to have 3 roots of the characteristic equation in the complex plane, counting multiplicity. So right now, we're just worrying about what happens when you get real distinct roots. So the roots are -1, +1, and 7. They're all different. They're all real. But it gets more complicated if you have the roots of, say, 5, 5, and 3. Or maybe the roots of 1 + I, 1 - I, and 7, right? So the roots of repeated or complex is more complicated. But in this case of distinct real roots, you get a general solution kind of like that from the 3 roots with 3 arbitrary constants in this case because it's third order. 3 initial conditions gives you 3 equations and the 3 unknowns, the 3 arbitrary constants in the general solution. You solve for those 3 constants, plug them back into the general solution, and voila, you have the solution to the IVP. Okay, I mean, it's not easy, but it is straightforward. And like I say, I could come up with some things, like if I change that to a 6, those 3 roots would just be some weird oddball irrational numbers, and you wouldn't be able to carry on. So look, in all these problems, look for simplifying things. You have a quadratic, you hope it factors. A system with 3 equations and 3 unknowns, you got a few of them in your homework, and there's 2 of them, I think, and both of them have kind of a trick. This is the trick that for one of them, that these C1s and C2s come together, so I subtract those 2 equations, and C1, C2 goes away. You can solve for C3. All right. Well, goodbye. Good luck on this web work set. All right. Bye.